about some of their shortcomings. And I promised you that in the next, or in the 2 weeks after that, we'd be looking at 2 alternative theories that can help us understand the real complexities of skill acquisition better. Now, because sports scientists are not the smartest people in the world, we often borrow theories from others. And one of those theories is called dynamical systems theory, or dynamic systems theory, or dynamical patterns theory, usually called dynamical systems theory. And dynamical systems theory is actually borrowed from mathematics and engineering, and it is really good at explaining how really complex structures self-organize into really meaningful coordinative structures. Yeah, so we're going to be using dynamical systems theory in a very similar manner. But as we go through this, always remember that dynamical systems theory is really borrowed from mathematics. Yeah? So I'm skipping over all the mathematical calculations of how a dynamical system changes, but in the background, always think about, oh, this has been mathematically described before. Right, so what are we going to do is we're going to define what dynamical systems theory really is. We're going to look at how boundaries or constraints can influence behavior based on the dynamical systems theory. We're going to look specifically at complex motor behavior or complex systems. And then finally, we're going to discuss what the functional role is of variability within these models. And you'll see, as we go through the dynamical systems theory and the ecological perspective next week, these theories are basically standing by themselves, but then the week after we will merge them together into a new theory that then we will adopt as our new understanding of skill acquisition. So first of all, we're posing this dynamical systems theory in direct contrast to the traditional models that we used in the first lecture, so the last week we did. And dynamical systems theory, even though it's been described by mathematicians, it's been adopted by mainly ecologists or biologists to describe really complex control in neurobiological systems. What that means is dynamical systems theory has been used to describe how coordination emerges in things that are seemingly too complex to be coordinated. And we'll see some of these examples from biology as well as in human movement as we go. First of all, and this is I just drew that a second ago, right? This is my ugly kid's drawing. But remember when I told you that there is no linear relationship between performance and practice time? Well, dynamical systems theory is really good at explaining why that behavior is nonlinear. Why there is a plateau phase followed by an increase in performance, followed by a plateau phase, followed by a decrease, followed by a plateau phase. And it's much better at understanding the complexities of how we react to practice or how our performance reacts to practice. And so keep that in the back of your mind. As I'm describing dynamical systems theory, we are really thinking about a nonlinear concept. Yeah? Right. So dynamical systems theory poses a few, or requires a few assumptions. First of all, it says that the learner is a complex biological system that has many independent but interacting subsystems. What that basically means is that, for example, we as movers, our body, while we move around in space, consists of many different segments, many different degrees of freedom that are all independent. We can move each body segment independently, but all of these body segments can interact to create coordinative behavior. And we call that a complex system. And that is a definition of a complex system. Furthermore, dynamical systems theory says that we've got this amazing ability to self-organize. And what that means is that even though we are a complex system and we consist of all of these independent and interacting degrees of freedom, we possess the ability to create coordinated behavior by self-emerging or self-organization. Self-emerging properties or self-organization. Furthermore, dynamical systems theory also says that once you develop coordinated behavior, is constrained by the boundaries in which you have to perform the behavior. And we'll see plenty of those examples both from animals or biological systems as well as in humans. Sometimes you'll see dynamical systems theory being referred to as complex systems theory. And complex systems theory and, for example, chaos theory in mathematics are closely related because they all describe very complex, seemingly uncoordinated, unpredictable systems. Okay. So we've got to ask ourselves a few questions. If you want to understand how dynamical systems theory can provide a different approach than these traditional models, we need to understand is why complex systems, or why understanding that a system is complex is so important for understanding dynamical systems theory. Also, if this is a theory that has been adopted by biologists and neurobiologists, etc., how can we fit human performance into that? How can we view human performance as a potentially complex system? Also, if complex systems spontaneously self-organize, that means we have to find some of these self-organizing properties in our skill acquisition process. Okay? And then finally, if we want to show that dynamical systems theory is important for understanding skill acquisition, we need to find that our coordinated behavior is constrained by the boundaries in which we perform that behavior. Yeah, so we've just applied what I said here is important for dynamical systems theory, and from that we've developed some questions that we need to answer if we want to understand how we can use dynamical systems theory to explain skill acquisition. So, first of all, complex systems are highly integrated systems. Yeah, so they're highly interdependent, and they consist of many parts that are both independent but interact. Yeah, we've already said that, and they have very specific characteristics, and I'll describe those characteristics, and then we'll try to apply that to an example. So first, we've already said, any complex system has many independent and variable degrees of freedom. There are many different levels within a complex system. Every complex system has the potential for nonlinear behavior, and just like we described the skill acquisition process before. Every complex system also has the capacity for stable or unstable patterned relationships, what we call coordinated behavior. And then finally, subsystems within a complex system have the ability to set boundaries for other subsystems, to influence those subsystems. I know that sounds a bit abstract now, but let's try and apply that to a few examples. When we try to understand the complexity of a complex system, in motor control since 80, 90 years, we've been talking about the degrees of freedom problem, and specifically Bernstein's degrees of freedom problem. And what the degrees of freedom problem says is that because we use all of our limbs, all of our segments, all of our muscles, we use our central nervous system, we use every aspect of our body to interact with our environment, that makes our body, per definition, extremely complex to orient within our environment. Yeah, think about it. If you take a broomstick, right? A broomstick has no degrees or 1 degree of freedom. You put it down and you release it and it falls down. Yeah, for a broomstick, these things are really easy to calculate. If it leans a bit to the right, it's going to fall down there. Leans a bit to the left, it's going to fall down there. But think of your body, just to maintain postural stability, you've got to contract different muscles together in order to just stay upright. Yeah? Even just standing upright is a really complex problem for our central nervous system. So Bernstein's degrees of freedom problem says, well, if our body is so complex, why is it that we can control all of these degrees of freedom in order to execute purposeful movement? And Bernstein's degrees of freedom problem has commonly been used in the field of motor development. And I asked the question to a few groups yesterday, but when you think about how a baby grasps onto an object, they grasp like this, right? And all they are doing is they are trying to minimize the degrees of freedom that they need to control in order to grasp onto an object. while an adult has amazing fine motor control. They can grasp onto a small needle, yep, by using their fingers. That means that as you develop this amazing ability to release all of these degrees of freedom and create much more versatility in how you can move. And this is a really interesting way in which we can understand Bernstein's degrees of freedom problem. That to become more skillful, you have to release and control more degrees of freedom. So in other words, the more complex you become, and the better you get at controlling that complexity, the more skillful you become. Okay? Of course, there are plenty of complex systems, especially in biology and ecology, and let's try and collectively describe some of the attributes that we've talked about, and let's try and apply them to some biological systems or a geological system. Let's take the ducks flying in a V, right? If we say that ducks flying in a V consists of a complex system, or is a complex system, that means it needs to have many independent and variable degrees of freedom. Is that true? Do ducks flying in a V, do they have independent and variable degrees of freedom? Yes, what are the degrees of freedom in the duck V?
Well, the position orientation of each duck.
Yeah, that's right. The ducks, let's describe them as the ducks themselves. The ducks themselves could orient in any different formation they want. Right? There's no single duck saying, hey, let's fly in a V. Right? They can orient in any formation they want, but they do it by patterning their relationships so that they have an optimized flight pattern against the wind. They are flying in a V because the wind pushes them to fly in a V. And they automatically self-organize in a very economical patterned relationship. So we've already said they have independent and variable degrees of freedom. There is the capacity for patterned relationship. What are the different levels within the system of ducks flying in a V? What are some of the different levels? What are some of the different aspects? What make those ducks, or what makes those ducks fly in that V and not another V or a bunch?
So are we talking about things like preventing winds and that sort of thing?
Yeah. Yeah. So the harder the wind blows, the longer the V becomes. Right? If there's almost no wind, then these ducks can actually fly in a row. And that seems like a silly explanation of dynamical systems theory, but it shows you that biological systems actually spontaneously self-organize into these highly patterned relationships. No single duck is making the decision to fly in a V. They are flying in a V because they are forced to do so by the boundaries placed upon their behavior. Yeah? The wind blows harder, they use a different V. The wind blows softer, they might not have to fly in a V after all. Let's take a weather system, right? Let's describe this. What is the potential for nonlinearity of behavior in a weather system? Why is that a nonlinear system? Remember, a linear system describes the linear relationship between a control parameter and the order in which the behavior appears.
Lots of variables affect weather.
Yeah, that's right. There are so many variables that affect weather that your air pressure can rise and rise and rise and rise, but it does nothing to the actual weather system because it might be counterbalanced by other aspects of the system. This is a complex system in itself. It spontaneously self-organizes under environmental boundaries. Yeah? These concepts of understanding complex systems are vitally important for us to understand why skill acquisition itself, or the way we use our body, is a complex system as well. Because our body has exactly the same properties as some of these other neurobiological systems. Right? Because we have many interacting and many variable independent degrees of freedom. Right? We have many joints and segments, etc. We have all kinds of different subsystems. Right? We have neural, hormonal, biomechanical levels that all act upon our body and all interact with each other. Right? Then, can we we spontaneously get that self-emergence of patterned relationships in our body? Of course. How many people have you seen who walk like that? Right? Almost no one, because it's an uneconomical way to walk. We automatically, spontaneously self-organize into this really economical pattern of walking, where our legs and our arms move asymmetrically. Different subsystems within our body can actually limit other subsystems, right? Cardiovascular endurance limits the performance of skills. The more tired you are, the more difficult it is to perform a skill with high accuracy. And so we know that they also interact, and on top of that, there is that amazing capacity for nonlinearity. It's not because your cardiovascular endurance increases that you get the same increase in performance results on, let's say, a triathlon. It just doesn't work that way. There's an inherent nonlinearity in that behavior because there are so many other things that act upon this complex system. Yeah, so our body, just like any other neurobiological system, is a complex system. It has all the hallmarks of a complex system. But how do we describe complex systems as dynamical systems? Well, dynamical systems, or when you try to describe a complex system as dynamical systems, or a dynamical system, what you're doing is you're saying that coordinated behavior can emerge, then disappear, emerge again, disappear, emerge again. It is dynamic. Yeah, so it's a dynamical system. And I'll try and explain that using ants. Yeah? Imagine sitting in here, or being an ant and standing in the middle there. Do you think that you'd see lots of coordinated behavior? If you were an ant, what would you think? What a mess. Complicated, what a mess. But the more you zoom out, the more you start seeing that some ants are moving towards the nest, while others are moving somewhere else, and other ants might be excreting some sort of hormone that's attracting other ants, and some are defending the nest. The more you zoom out in a complex system, the more you see its macro coordination. Give you another example that you've all encountered before. Who takes the train to school? Yeah? If you get off at a busy station, right, and you're standing in the middle of town hall, and everyone's going left and right, you think, oh, what an absolute mess. But when you imagine zooming out all the way out, and you'd look at it from the top, you'd see, well, these people are running because their train's leaving in 4 minutes. These people are really slow because they're old. These people are not moving in a straight line relationship because their perceptual information is poor. All of a sudden, when you zoom out, you get this amazing view on how coordinated this behavior actually is, and whether or not that is in a biological system like an army of ants, or, in our bloodstream, and we can see that macroscopic coordinated behavior everywhere. And what we actually see is we see a constant organization and reorganization of those coordinative patterns. Yeah? So I was at that. So these complex systems have a seemingly very random organization. When you stand in the middle of it, it looks like they're not coordinated at all. But actually, because there's a potential for a lot of order and disorder in the system, because of its degrees of freedom, etc., when you zoom out, all of a sudden you see that the degrees of freedom in that complex system spontaneously self-organize under the boundaries of the environment. So, showing how coordination occurs in a complex system as a matter of organization and reorganization is what the dynamical systems theory does best. Yeah? And for those of you who did that last year, you would remember that the property, or what, if we were to describe the dynamical systems theory in a few words, we would say dynamical systems theory tells us that with a linear increase in a control parameter, you get a nonlinear increase in an order parameter. Yeah? And that's really what you see here. Behavior is described as being nonlinear in the dynamical systems theory. Something that's closer to your heart, let's say. Who hates watching soccer? A few, right? You might have said, once in a while, you might have said, I don't understand, what are they actually doing? They're just 11 guys running behind the ball and it seems like no one knows what they're doing. Right? The first time I watched Australian football, I thought exactly the same. But in fact, what we see when we zoom out is that there's actually huge amounts of macroscopic organization. If these midfielders move up, these forwards move up, these defenders move up. When we attack, everyone expands, while when we defend, everyone contracts. Even within a system like that, there are many independent but interacting degrees of freedom that all self-organize into coordinated patterns. Okay? So, a complex system is or complex systems theory and dynamical systems theory is a really interesting way in which we can describe the self-emergence of coordination in complex systems. Okay? Let's apply dynamical systems theory. We said dynamical systems theory describes the organization and reorganization. Now, most of the work I do as a researcher with dynamical systems theory is on team sports, and mostly Australian football, but a lot has been done in soccer. And what they see is that, in fact, a soccer team behaves just like a complex system or a dynamical system because it contracts in defense, expands in attack. Contracts in defense, expands in attack. And the faster the opposition team counterattacks, the faster you have to contract. So it's governed by the boundaries of the environment that influence how coordinated the system needs to be. Okay? So, what does dynamical systems theory do? Well, first of all, it says that we gradually transition from one coordinated state into the next. And you've heard that term yesterday, we call that attractor states. Stable attractor states. So when someone coordinates their body to perform a certain drumming movement, and it starts to become economical and you start having fun and you're able to do other things at the same time, what you're doing is your central nervous system is self-organizing all of your limbs and body segments into a stable attractor state. That attractor state can stay, but it can just as well disappear, reappear, and disappear. Right? Dynamical systems theory. And there are multiple of those states of organization. And in fact, the better you get at drumming, the more of these attractor states you develop. And that is what we say as skill acquisition researchers, why dynamical systems theory is so important for understanding expertise. Experts have developed this amazing ability to develop attractor states that appear and reappear whenever they need it. In other words, they're economical in a wide range of that task. Okay? For example, and also, or a good way of describing that dynamical systems theory I told you is by understanding the boundaries, right? For example, when someone is running, right? The reason why you run in a particular way, and you run different than me, and you run different than me as well, why we all have individual ways of running, is because our central nervous system has this amazing ability to self-organize our degrees of freedom based on what we need as an individual. If you have short legs, you're running different than when you have long legs. If you have zero flexibility like me, you run very differently than when you have lots of flexibility. So our body is amazing at organizing degrees of freedom to produce coordinated movement based on our own movement signature. And that is why dynamical systems theory is so important. If you looked around in your classroom yesterday after the drumming, you would have seen vast amounts of inter-individual differences in your drumming performance, right? There is no way we can apply these traditional theories and say, well, everyone learns the same, right? It all looks very similar. No, if we can apply dynamical systems theory, all of a sudden we've got this really strong point to make that some people learn at a faster rate than others because they self-organize in a different manner. And of course, you've done this yesterday, so I won't reiterate that, but a really good way of testing what you know about dynamical systems theory is to look at what's called moving in their first year of life, all they are doing is a tractor state occurs, it disappears. A tractor state occurs, it disappears. Now they're crawling, now they're sitting. Now they're crawling again, and they're trying to pull up to something. Now that disappears. Now they're crawling again, and all of a sudden they're standing. Yeah, so motor development is a constant organization and reorganization of these attractor states. And when you practice your skills project, you will feel exactly the same thing. At some point, you will feel something click. And when it clicks, it means that you've developed that stable attractor state. You've become reasonably economical. You've developed a basic coordination pattern that kind of feels good. It might not be the best after all, but it kind of feels good. Yeah? And the more you practice, the more you strengthen either that attractor state or you use it to develop another attractor state that's maybe more beneficial. And what's great about that is, imagine if you were training for a specific track and field event, right? Some shot put or whatever. And then you're a 13-year-old male or an 11-year-old female, right before their growth spurt. And you're getting amazing at this technique, right? You're always winning all of your competitions, etc. All of a sudden you grow 8 centimeters a year. Your body has changed completely. If you've used, or if you've learned to use an idealized technique, then you're going to keep using that technique even though you're, let's say, 10 centimeters longer and your arms are this long all of a sudden, and you're going to decrease your performance. But if you've applied self-organization and you've taught your body to self-organize, then all of a sudden when you start growing, you've developed this ability to forget your old attractor state and build new attractor states on that old attractor state. And that's a really important thing to understand when we talk about adaptability and expertise. So, just applying that, or we already did that, we already applied how states of organization occur, but we didn't really use that term constraints very often. You can replace constraints by boundaries, right? When I talk about boundaries, I talk about constraints or vice versa. And what we say in dynamical systems theory is that the coordination that exists within a complex system is governed by the boundaries or the constraints that act upon that system. And ultimately, skill acquisition is being able to produce a particular motor skill even though different types of constraints are acting upon it. And you could do something when you're fatigued just as much as when you're fresh. You can execute a skill when you're in pre-season 5 kilos lighter than when you're in the middle of the season 5 kilos heavier. I don't know how that, if that works, if it works that way. I've never done a pre-season or post-season. I get 5 kilos heavier every year. So what that does is it helps us in adapting our movements as constraints or different constraints start to interact upon how we perform that movement. And so all of a sudden we're talking about a really adaptable behavior. And I don't know why I put that in there twice, but basically same thing, you can apply that again to motor development theory using these milestones. Right? So if you want to practice using dynamical systems theory, try and go through why a baby develops all of these behaviors. And I'll give you a hint here. What do you think is the reason why a baby goes from this behavior, lying down, to the pushing up on elbows? What is the constraint that acts on this coordinated behavior? Why does pushing on the elbows, it's not a learned behavior. You can't learn a baby like that, anything similar to that. Why does it self-emerge? Sorry? Sorry? Yeah, to look around, but what is the individual, the reason within the individual why it's able to look around? That's all it is. A baby has a massive head, right? We all know that baby has a massive head. To lift up that head, you've got to have quite a lot of neck strength. It's not until you develop that neck strength, which is an individual constraint, that allows new behavior to emerge. And you can think of babies learning to walk in that same way. Yeah, so practice that for yourself when you're practicing for your oral examination. And constraints can be physical, or they can be informational. Physical constraints are things like functional constraints, for example, your perceptual abilities, and how good your eyesight is, that sort of stuff. Or they can be structural, for example, your hand size or your grip strength. But constraints, and we'll see this next week, can also be informational. They can also be directed by energy flows in the environment. And when I talk about energy flows, I don't talk about the hippie kumbaya stuff. Yeah? But what I'm actually talking about is that energy exists in the environment around us. We pick that up as perceptual information. Right? So perceptual information can form a constraint for behavior or the emergence of behavior. So, dynamical systems theory is pretty good at explaining why a macroscopic coordinated behavior emerges in these complex systems. Because complex systems settle into attractor states, economical attractor states, coordinated states that are beneficial to them at that particular time. Okay? But achieving and maintaining stability in these complex systems is really difficult. And so I've worked for 3 years with a particular team working around how can we design training environments in which we can have this behavior self-emerge. And it's a really, really difficult thing to do because even a small change or a slight change in the personnel that's available completely reorganizes the coordinative state that you've worked really hard for to establish. And so achieving and maintaining stability is really, really difficult. Okay? Take this picture, for example. If you'd be one of these ducks, you would never see the organized behavior that's actually exhibited by this pack of ducks, I don't know how you say it, a group of ducks. But if you zoom out, all of a sudden you can see that their behavior is constrained by the current flow, or by the strength of the waves, etc. And they're only patterned in this particular relationship because this gives these ducks nothing to do. They can be incredibly lazy, and those ducks are working hard, but most of the group or the pack of ducks can be really economical. And for their system, this is the most economical system in which they can exist. Right? So this pattern self-emerges under the influence of constraints. And of course, another, and we've already looked at this in motor learning, but if you haven't looked at that yet, a really good example to try and apply dynamical systems theory is to the walk-to-run transition. And it is so interesting because if you gradually increase the velocity with which you move, and you are increasing linearly a control parameter, you get a nonlinear increase in order states or attractor states. And so if I gradually increase my velocity, at some point I'm transitioning from walking into running. I'm going from coordinated walking behavior, even though my speed increases, and at some point I just abruptly switch to coordinated running behavior. It is a nonlinear state, nonlinear change in an order parameter as a result of a linear change in a control parameter. And you can think of many complex systems within dynamical systems theory in a very similar way. They are affected by a control parameter, but they only change state after a certain threshold is reached. And for those of you who've done this already, you don't have to do it again, but those of you who haven't, we can do Kelso's finger wagging experiment, which was the very first experiment that was done in understanding how dynamical systems theory explains behavior from a motor perspective. So all you need to do is, I'll show it on this slide, it's a bit better. All you need to do is first start moving your fingers in an in-phase pattern, and then gradually increase the speed with which you move your fingers, and you'll see, I'll just do it deliberately, but you'll see that first you move them in phase, then they become some sort of intermediary phase, and then all of a sudden, as you start moving faster, your fingers start moving out of phase or in an anti-phase pattern. And why that's interesting is because it shows exactly the same nonlinearity in behavior as we described before in the walk to run transition. A gradual increase in the frequency with which you move your fingers leads into a non-linear change in the order parameter, antiphase or in phase. And these are the very first fundamental experiments that established that coordinated behavior appears and disappears as a result of its environment. Just like when you're a skier, your body position changes drastically, or the coordination pattern that you use when you're skiing changes drastically based on whether you're skiing on powder or on ice, for example. You're using very different coordination patterns when you're doing either of those. You have the ability to use different attractor states that you've learned to interact with your environment. And that's a great way of describing why we are so versatile in interacting with our environment, and why we can constantly adapt to changes that exist within it. Sorry. So, in those traditional models, of course, we lacked a lot of ability to describe the complexity of skill acquisition, right? Because all we basically said was that perceptions and memories and intentions, motor skills themselves, are basically captured somewhere in the central nervous system, and when you need them, you're grabbing one of them and you're executing it. Okay? Dynamical systems theory adds a lot of complexity to that and says not only do you spontaneously self-organize as a result of how you interact with your environment, but also we can describe skill acquisition as a complex system and actually get a theory that's reasonably good at explaining how this complex system organizes into seemingly coordinated states of behavior. And you've seen this yesterday, the most prevailing or the most prevalent model that explains how functional coordination patterns emerge as a result of a coupling between perception and action is Newell's model of constraints. And it says that this behavior is influenced by your environment, the task you are performing, and you as an individual. Okay? To give a bit more insight, a coordination pattern can be affected by whether or not you've got a visual defect or not, by your genetics or by your technique, but also by your cognitions, your memories, your experience, etc. And so it can be influenced by individual or organismic constraints. And it is very likely that two people with a different kicking technique are going to exhibit a different coordinated pattern. Yeah, that coordinative pattern is constrained by the boundaries that act upon it. Same thing for environmental constraints. We know that you play different in high altitude versus low altitude, or on sand versus on normal surface, etc. We automatically self-organize to the boundaries that our environment places upon our skill. And then most importantly for us is we can actually design environments in which we only allow people to self-organize in a specific manner. For example, what happens when the hoop for children is lowered? Rather than being really high, what happens when it's lowered? Which kind of coordinated behavior emerges in children, do you think? Child is practicing on a high hoop, right? One that we've got in the sports hall, and practicing and practicing. All of a sudden someone comes in and says, no, this is now how we're going to organize the rules of the game. The basket is lower. Which kind of coordinated behavior is going to emerge? What is going to change? How is it going to influence the complex system of shooting a basketball? Yeah, they'll score more, right? That's the first thing, they'll score more. Yeah, so automatically we know whether you've got a high ring or a high basket or low basket, you're going to use a different coordination pattern to achieve the actual task goal. Okay? Same thing with changing the task goals in a small-sided game. Or, for example, let's take the second one. What is the coordinated pattern or the skill pattern that's going to emerge when you higher the volleyball net versus lowering it? which coordinated behavior is going to self-emerge on a high net that doesn't emerge at a lower net.
Jump higher.
Yeah, jump higher, and let's say they're kids, right? Let's say they're kids in this case. Yeah, that's right. So when you have to throw a ball over a net, what does that automatically give the opposition? More time. So this is a great way in which you can influence someone's behavior by understanding that their coordinated behavior self-emerges as a result of the task constraint that you placed upon them. And it's a really, really great way to think about skill acquisition, because all of a sudden, you don't have to tell someone to throw the ball higher. No, you can create the environment in which this skill self-emerges. And we'll see later on that self-emergence is an implicit way of learning. And an implicit way of learning is very robust under stressful scenarios. Right, so this is a really, really powerful way to use skill acquisition. What about the first one? What if we make someone run on a downward slope while they're practicing for their sprinting training? I don't know anything about sprint training, but you can tell me. I've seen it happen a few times. Which coordinated behavior will self-emerge in the runner?
They'll speed up their legs.
Yeah, that's right. So they'll get a higher step frequency, and we know a higher step frequency can be useful for sprint training. I don't know if it is, but this, just applying these constraints to practice, automatically makes certain behavior self-emerge. And when you control that ability to make behavior self-emerge, you've got a really powerful tool to design practice environments in terms of skill acquisition. And in fact, when we look at skill acquisition or the skill acquisition process, the better you get at dealing with new constraints, the more skillful you are, or the better you have acquired a new skill. Therefore, within your skills project, your transfer test essentially is going to be the introduction of a new constraint, and I'm looking at how you deal with that new constraint, right? And of course, these constraints can interact. If we look at this example, if we emphasize, let's say, or if the climbing surface for that climber changes, how will their coordinated behavior change? Let's say that rather than a rather rugged climbing surface there, we get a reasonably smooth climbing surface. How will their coordinated behavior change?
Slow down.
They're going to slow down. Yeah, very good. They might use another type of grip. What if we tell them that we're going to change the task constraints? Rather than just climbing up, we're going to make them climb up as quickly as possible. How is their coordinated behavior going to change?
Well, they're probably going to climb faster.
Yes, and they're going to make more errors, take more risks. We get an entirely different coordinated behavior just by applying a task constraint. If you now apply a task constraint and an environmental constraint, well, you basically get death if you do those two. But I mean, you can see how coordinated behavior changes when constraints interact. Okay? And the same thing happens with babies, right? By sitting a baby down in this particular, whatever it is, floaty device, whatever it is, and they sell all kinds of things these days, what you're doing is you're slowly actually making this baby accustomed to sitting upright. And you're creating an environment in which it is beneficial for this child to sit upright. Eventually, that might transition into this type of behavior where a baby sits upright by themselves because they've developed postural muscles to sit like that. Okay? So you can create environments in which certain behavior eventually self-emerges. What is the great thing about sitting upright while you can't really sit upright yet as a baby? What do you get when sitting upright versus lying down? Sorry?
Works the neck.
It works the neck, but what else? There's something great we have as humans, yeah, and it sets us apart from lots of animals. Yeah, manual dexterity, right? And the faster you do this, the faster they can start grasping objects. Yeah, so I don't know if that's how it works, yeah, but there's a real theory behind if you constrain an environment, certain skills will self-emerge. If you free up the hands, coordinated behavior will self-emerge. The same thing There are plenty of drummers, well-known drummers, who are missing a limb and they play exactly the same way as someone else. That means, given their organismic constraints, they are able to produce very coordinated behavior in a similar fashion to someone who has both arms available. And then, coming back to that degrees of freedom problem, when we think of our body as a complex system, skill acquisition is actually the ability to coordinate as many aspects of that complex system as we possibly can. For example, here this person is really good because they are even able to control how they are pointing their toes versus a soccer player who looks a lot less coordinated. Yet this person is freezing more degrees of freedom and this person is releasing more degrees of freedom. And the way in which we deal with that complexity of our body, or the way the central nervous system deals with it, is by creating functional linkages. And you've heard that term used before, but what they basically do is what you did yesterday in drumming, is they freeze certain degrees of freedom, so they act as one degree of freedom rather than all types of separate segments. And once we understand what a complex system is, we know that if you freeze these degrees of freedom, you are decreasing the amount of independent and interacting degrees of freedom that exist within your complex system. So we said that. The first time you were driving, you were probably very, very tense, and then now you can drive with one finger on the steering wheel, with the pinky on the, what's that called? That shape?
Gear stick.
Yeah, gear stick. Same thing when you watch those people at Maroubra who do the surf school thingy. When they're jumping up, they're all like stiff and everything, but then you watch a pro surfer and they're very smooth. Freezing the degrees of freedom to solve the degrees of freedom problem, releasing the degrees of freedom to solve the degrees of freedom problem. And same thing with a soccer kick, especially if you compare that to a kid kicking a soccer ball. Young kids kick like this. Freezing all degrees of freedom except the hinging in the hip, and all they do is this, right? While an expert player really releases all of those degrees of freedom. You can read up on this study if you want. This is not working. This is a study using a ski simulator, and what they did was they placed subjects on a ski simulator and they saw that the white squares there on top, when people started out, they had a very small amplitude of movement, they were freezing the degrees of freedom, but as they practiced more, they developed more expert-like coordination patterns, they released their degrees of freedom. And so it's a well-established phenomenon that early in practice you freeze degrees of freedom to solve the degrees of freedom problem, and later on in practice you release those degrees of freedom. But, of course, it's not all about in the beginning of learning how to freeze degrees of freedom. Releasing them is actually a really, really important attribute, and it's especially important when you think of adaptability. If you imagine all the kinds of different table tennis shots you can do, then we know that the more adaptability in that behavior that you can create, while still maintaining the same output, the more skillful you are, and that's called degeneracy. And we'll see that using this example, I'll just skip through to it here, is if this is the movement of a paddle until time to contact for expert players, then we see massive amounts of variability early on in the movement, but almost no variability at the point of contact. Why do you think there's so much variability here and so little variability there?
Because you wanted to contact in a particular way, so the ball goes where you want it.
Yeah, you need consistency.
But it can start anywhere.
Yeah, that's right. And that is a really cool feature of experts. They can harvest this variability in enormously specific ways. Right? They can have all of this variability here, but still end up with a very consistent end result. Okay? Because too much variability there would obviously lead to very errorful performance. You can have a read over this in your own time because we're running out. I'll just show you this in the next slide, which is the way in which you can see that variability in action is even if you compare two of the best sprinters of the last decade, they have very, very different sprinting techniques. And there's inherent variability in movement that we need to capture. If we want to do skill acquisition, we need to capture that inherent variability in movement. And that variability is often demonstrated in skills that seemingly are highly unvariable. And so, for example, in rifle shooting, very static scenarios, we see that these rifle shooters, they're extremely precise. Right? They are very, very good at shooting from a long distance at a very, very small target. But when we measure how much variability they have in the wrist, the elbow, and the shoulder joint, there's actually a lot of variability there. They are constantly moving, but they are constantly moving in such a way that they can create consistency here. So whether it's table tennis, and you've got huge variability early in the movement and no variability at the end, or it's the massive variability that you create in the shoulder, elbow, and wrist joint that results in really consistent performance here, harvesting movement variability is a really important concept within dynamical systems theory. So, in summary, we looked at dynamical systems theory, why it's useful. We looked at the degrees of freedom problem and how that's helpful in describing our body as a complex system. And we looked at Newell's model of constraints, which you'll see not next week, but the 2 weeks after, and which we'll use as a framework for the constraints-led approach to skill acquisition. And we've looked at how dynamical systems theory can help us explain why so many experts, even though they're producing the same outcome, do it in a vastly different way. All right? Any questions come up front? If not, I'll see you next week